Bismillahirrahmanirrahim. Assalamu alaikum dear students. I am Mr. Kadim Khan and I am a lecturer in the Institute of Computing, Kuwait University of Science and Technology. Today we will take lecture number 18 of the subject of Introduction to Computing, in which we will discuss the number systems of the computer. Dear students, computer uses a certain number system to store the data and also to process the data. The number systems are in fact a certain numbers which are understandable to the computer. When we type certain words inside the computers, then the computer converts that words into a certain number, and that number is in fact understandable to the computers. The number system of computer system is very much important because when you want to do a programming, then you must be aware of the number systems of the computers. So that's why this topic is very much important. This is the discussion agenda. It contains the topics of the number systems. Then we have the types of different number systems, including decimal number system, binary number system, octal number system, and the hexadecimal number system. So these are different number systems used by the computer. Basically, at lower level, the computer uses the binary number systems, while we humans uses the decimal number system, also the octal and hexadecimal number system. But these number systems are converted into the binary number system to store the data and also to perform a certain operations over that data. And at the end, we have the number systems relationships, that what are the relations of these four different number systems with each other. So these are some important topics that we will cover in this lecture. What is the number systems? Basically, the number systems are certain techniques which are used to represent certain numbers in the computer architecture. The computer uses this number system to process the data. This number system may represent certain data as well. And also these number systems are used to represent the commands or the operations of the computers. So that's why the overall architecture of computer is defined using the number systems. Every value in the number systems that we stores or saves in the computer memory has a certain number systems. For example, important system used in the computer number system is called the binary number systems. In the binary number system, we have only two digits, either 0 or 1. So these two digits are used to represent the different instructions as well as the data inside of the computer memory. And these number systems are also the building blocks or the main components of the system architecture of the computer. Because arithmetical and logical units and the control units understands the data when that data is only in the binary number systems. So the computer must convert the actual data that has been typed by the user into this binary data, and then this binary data is processed by the computers, and then back after the processing, that binary values are converted back to the user understandable format. So that's why number systems are very much important to the computers. The number systems are very much important because this helps to design the computer systems, and it depends on the number system. Basically, in the designing of the computer, the binary number system is mostly used. And also you can use the hexadecimal and other number system as well. So when we want to perform the assembly language programming, then we use a certain number systems here. So when we type some words or letters inside the computers, then the computer translates that words or letters into a certain numbers which are only understandable to the computer. For example, here when we type a character A, then the character A is converted to the ASCII characters, and then ASCII character is converted to the binary characters to represent the character A here. Similarly, all other numbers, digits and symbols are also converted to the binary digits. So that's why computer converts all these characters or words or numbers and any other symbols to the computer understandable formats. For that purpose, number systems are very much important. Computer understand the positional number systems, where there are only few symbols that are called the digits. So the position of the numbers is also very much important. For example, the first number defines the signs of the number. For example, if it is the 1, that means that it is a positive, or 0 means that it is not positive. So the position of the numbers also defines the number systems. So here, each and every number system is determined using the digits. The digits is a certain values which is in fact used to store the data or to represent the data. And the position of the digit in number system is also very much important. For example, if the value is assigned, then it means that we will understand the values of that particular number system by the signed values. And the signed values in fact indicates that this number system or this number is the positive or negative. Also, we have the base number of the systems. The base number defines that what types of categories this number system is representing. For example, for the binary number system, we represent 2 as a base. And similarly, for the decimal, we represent 10 as a base. And for the octal number system, we represent 8 as a base. And similarly, for the hexadecimal number system, we represent the base 16. So these are used to define the total numbers of digits available in that particular number system. Now here we will discuss each and every number system in the details. We have 4 important different number systems: decimal, binary, octal and hexadecimals. Here we will provide each and every number systems in the details, and also we will provide you the examples of these number systems in upcoming slides. Now, the first number system is called the decimal number systems. The decimal number system is mostly used by the humans. Also, it is used by the computer as well. But when we type certain values, then value will be typed in the decimal number system. The decimal number system, as its name indicates, it has the base 10. Because decimal deca means tens. So that means that there are 10 numbers in the decimal number systems. And these 10 numbers are from 0 to 9. So it includes 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9 values. So these values are in fact used to store the values inside into the computers. Each and every numbers in the world is composed of the numbers from 0 to 9. Now this means that the numerical quantity can be represented using these 10 digits. And the decimal number systems is also called the positional number system because there may be either negative or positive number systems. So it depends on the position of the number systems. And then decimal number system, that is also called the positional number systems, means that when the value of the digit will have certain position, then it depends on the particular number system. For example, if we change the position of this 0 and 1 with each other, then the value of this number will also be changed. It will become 1. So that's why it is called the positional number systems. There are certain examples of the decimal number systems. For example, 734 is one of the decimal number systems. Similarly, 971 is also another decimal system, and 207 is another decimal number system. In 734, we have the values of the 7s, which is 700, which is equal to 7 double zeros, that is 700, or it can also be represented through multiplying 7 with hundreds. So 7 multiplied with hundreds, or 7 multiplied by 10 raised to the power 2, because 10 raised to the power 2 represents 100. Though 734 is equal to 7 multiplied by 10 raised to the power 2 plus 3 multiplied by 10 raised to the power 1 and 4 multiplied by 10 raised to the power 0. So while computing all these three values, we can in fact compute the values of 734. So 734 is representing here to certain expressions here, which is a certain formulas of mathematics. Now 971 has the value of 7s is 7 tens are equal to 70. So 7 tens means that here's the 7s is the 10th value in this whole number, are equal to 7 multiplied by 10 are also equal to 7 multiplied by 10 is power 1. But when we have the 1 power of 10s, so we don't write 1 here. Now 971 is equal to 9 multiplied by 10 is power 2, which is 100, plus 7 multiplied by 10 is power 1, which is 10, plus 1 multiplied by 10 is power 0, which is also 1. So that is equal to 900 plus 70 plus 1, which is equal to 971. Also we have 207s, and this value is 7 units are 7. So this is the value of 7 is 7 units are 7 multiplied by 1 are 7 multiplied by 10 is power 0. So here the 7 value is in fact 7 just. Now 207 is equal to 2 multiplied by 10 is power 2. This is 200, and 0 multiplied by 10 is power 1, which is equal in fact the 0. And this 0 representing the 10 digits, and 7 multiplied by 10 was 0, which is only 7. So 200 plus 7 is equal to 207. Now the weightage of each positive number can be represented as hairs. That is means that, for example, positive numbers can be represented with a 10 raised to power 5, 10 to power 4, 10 to power 3, 10 to power 2, 10 to power 1, and 10 to power 0. So these are some examples tables for representing the decimal numbers here. Now this is a number which is expressed in terms of different decimal numbers. For example, 17.591. Here this one's, which is here, the most significant digits is 1, which has the 10th value. And similarly 7 is another which has the 1's value. Here is the point. Now 5 is in fact multiplied with 1 divided by 10, so this is the 10th, also 10th value. This is 100 value, but its value is not 100, but it is 1 over hundreds. And similarly it is 1 value which is 1 over thousands, because it represents 0.001. So that's why this is 1 over thousands. So here 10 beggars and 10 smalls means that here we are in fact going towards the right positions, which is 10 times smallers, and here 10 times beggars. So means that 10 is multiplied with here. So for example, this is the 10 digits, so 10 multiplied by 1 multiplied by 10 is equal to 1, 0. Similarly here we will just multiply 7 multiplied by 10 is power 0, which is 7 here. So this is the representation of the decimal numbers by using the most significant and least significant digits in the decimal numbers. Another important representation of the number system of computer is using the binary number systems. This is quite easy way to represent the instruction into the electrical signals of the two-state systems, that is either on or off. Here we represent the binary number systems to represent the electrical signals. The electrical signals of is in fact travels through the circuits in the form of the binary numbers, and here the electrical signals will be used through the two-state systems on or off. On means 1 and off means 0. So when the value is 1 passed, then the electrical signals is passed, and when the value is 0 is passed to the processor, that means off the electrical signal, means that no electrical signals will be provided through the circuits. Here on is represented as 1, and similarly off is represented with the help of this 0. So through 0 is not actually no signal, but signals at lower voltage. Means that there is the lower voltage signals, when means that 0. So 0 means lower voltage signal is provided. Similarly, the number system having just these two digits 0 and 1 is also called the binary number system. These are this is the important number system because computer understands only the binary number systems, not the other number system, because the computer takes the signals in the form of the electrical signals using certain circuits, and these circuits will be either on or off. So when one is paused, that means the circuit is on, and when the 0 is passed, then means the circuit is still on, but it is a lower voltage on. So means that just lower voltage signal is provided with the help of 0. The binary number system is also called a bit number system. Means that bit means that which is the lower memory representation of the computer systems. Here, the binary number systems has the positional value system where each digit has a certain value expressed in the form of the power of 2, and these are displayed here. So each value has certain power of 2. Now this is the examples of the binary number system in these tables. When we put the 0 means lower voltage, there is no certain values or nothing counts here. So starts at zeros means that nothing is available with us. When 1 then means just one item is available, so it is represented with just 1. And when we put the 1 0 in the decimal, this is the 10, but it is not actual 10, it is 2 in the decimals. So it means that 2 items. So starts back at 0 and but add ones to the left. So means that 1 is added. Next is in fact 11. That is 1 1. It is not in fact 11. It is just 3 here. So that means 3 items. And this is the 4. So 4 is in fact 4 items here. And similarly this is the 5. Similarly it is 6, 7 and 8 and similarly and so on. These are all different. This is the 10. So in fact and so on, these are different binary number system which represent certain values here. This is the equivalence of the binary number system to the decimal number system. Here are some equivalence values that are representing here with these tables. This is the decimal value 0, 1 to up to 15 and so on, and these are the binary values. For binary value of 0 is exactly 0. Binary value of 1 is exactly 1. But the binary value of 2 is equal to 10. So it means that here the 2 represents 1 0. So when we divide the 2 over 2, we will get the divisor is 0, 1 and the remainder is 0. So this why it is 1 0. Here it is 3. So 3 is represented with the 1 1. So when we divide 3 by 2, so the divisor is 1, and in fact the values, that is the in fact the values which is divides when we divide 3 over 2, so the answer will be 1 and 1 is the remainder here. Similarly, when we divide 4 by 2, so when we divide 4 over 2, that is equal to 2. So 2 divided by 2 is equal to 4. So here the in fact the 1 0 0 is representing 4. Similarly 5, when we divide 5 by 2, so here we will divide that 5 over 2 here. Now for example, I want to convert this 6 to the decimal number systems. So for this purpose I will take the pen. So here I will write 6 and then the divisions will start here. So start dividing 6 by dividing 2. So 6 divided by 2 is equal to 3. When we divide 6 over 2, then the quotient is 3 and remainder is 0. So there is no remainder. So 0. Again I will divide 3 by 2. So here I will write 2. So when we divide 3 by 2, so result is 1, while remainder is here is 1. So 6 is equal to, counting from here, 1 1 0. So 1 1 1. So we will start writing from this direction, then go to the upper direction. So this is 6 in the decimal number system, which has the base 10, is equal to 1 1 0, and it has the base 2. These are brackets, so its base is 2. So this is the techniques of converting the binary, the decimal to the binary. Now we will also convert the binary to the decimal, but that will be in fact performed in the upcoming lectures. Now the third number system is called the octal number system. As its name indicates, the octal number systems are certain number system which has the base 8, because octal means 8. So there are only 8 digits in this system: 0, 1, 2, 3, 4, 5, 6, and 7. So the octal number systems also used to represent the positional values with certain digits. Here, this number systems represent certain digits which has its values expressed in the power of 8. So these are have the power of 8. So 8 power 5 represents certain decimal number system: 8.4, 8.3, 8.2, 8.1, and 0. So these are different octal number system which are representing decimal number system. So octal number systems has the sum of the products of each digit with its positional values. For example, there are 7 to 6, 3 digits in the octal number systems. When we want to convert this octal number system to the decimal number system, we will find out the position of each digit. 7 to 6. So 7 to 6 is representing 3 different digits, and its base is 8, so that's why it is the octal numbers. Now 7 multiplied by 8 power of 2, because it is the third digit 7, but its position should be 1 less than 1 less values. For example, 8 power 2 plus 2 multiplied by 8 power 1, and similarly 6 multiplied by 8 power 0. So when we will I'll calculate these values. So it is equal to 448 plus 16 plus 6. When we will sum all these three values, the result will be 470 with the base 4, which is our decimal number. So 7 to 6 octal number is equivalent to 470 number with the base 10. So this is the decimal number here. So here, this is quite easy way to convert the octal numbers to the decimal number, but you just need to compute the power of all these values. The fourth and final number system is called the hexadecimal number system. As its name indicates, in the hexadecimal number system, we have 16 different values, and 16 different numbers are representing the decimal number systems. So these 16 numbers are the symbols which are used to represent the hexadecimal number system. Contains 0 to 9 values of the decimals, and A to F, which representing A for equal to 10, B for 11, and so forth, and F for the 15. So 0 to 9s and A to F different digits are the symbols are used to represent these hexadecimal number systems. The hexadecimal number system also has the positional value system, where each digit has a certain values which represents the power of 16s, and these are shown here. So when this is the fifth number, so when we convert the hexadecimals to the decimals number, then for example, if a certain digits or certain value is in the fifth position, then we multiply it with the 16 power 5. And if it's in the fourth position, so we will multiply it 16.4. And if it is the third position, we will multiply it with the 16 power 3. And similarly with this value are the finals, which is near to the exponent power point. So then we will multiply it with the 16 power 0. So the hexadecimal number systems has the base 16, so that's why we will multiply it with the particulars positional values and then multiply with these particular constants values and with the powers. Here is the example of converting decimals equal to the hexadecimal number systems, which is the sum of each products of each digit with its positional values. For example, here is the hexadecimal number system. Now, as we have mentioned that in the hexadecimal number system, there are the values comprising from 0 to 9, which are the digits, and symbol from A to F, which are in fact different symbols. A represents 10s, B represents 11, C represents 12, and similarly D represents 13, and E represents 14s, and F represents 15s here. So 27FB base 16s is equal to 2 multiplied by 16 power 3. Because there are 4 different symbols here, 27FB, so 1 less than the 4 will be the multiplication of 2 with the 16 power 3. Similarly, plus 7 multiplied by 16 power 2 plus 15 multiplied by 16 power 1, and the final, which is B, and it is in fact 10 multiplied by 16 power 0 here. So you can see here that 2 is multiplied with the 16, 7 is also multiplied with 16 power 2, and F is in fact the 15, so 15 multiplied by 6, in fact 16 power 1 here, and B represents 11 here. Now then we will compute these values. So 16 power 3 means 16 multiplied by 16 multiplied by 16. And 16 power 2 means 16 multiplied by 16. And 16 power 1 means just 16. And 16 power 0 means 1. So 1 multiplied by 11 is 11. Similarly, 15 multiplied by 16 is 240. This is 792, which is the computation of this expression. And 8192, which is the computation of 2 multiplied by 16 power 3. Now, summing all these values, we will get 10235, which is 10,235, and it has the base 10. So this is the decimal number which is equivalent to 27FB of the hexadecimal values. So this is the method of converting the hexadecimal numbers to the decimals here. Now this is the important tables which summarize all these concepts. That, for example, first we have the binary numbers, then we have octals, decimals, and hexadecimal. In the decimal, we have the digits from 0 to 9, so 0, 1, 2, 3, 4, 5, 6, 9. Next is 10, which is composed of 0 and 1, so this is 10, 11, 12, 14, 15, and so on. When we convert these decimals to the octal, so we will in fact convert that, we will write the same number values up to 7, but after 7, when it will be the 8, so then it will be 1, 0. Similarly, 9 will be equal to 1, 1, and 10 will be equal to 1, 2, 1, 3, and so on. And this is the binary representation of this decimals value, so 0 means 0, 0, 0. So 0, 0, 0 is in fact the binary values of this 0. 0, 0, 1 is representing 1. Similarly, 2 is equal to 0, 0, 1, 0. Because when we divide 2 over 2, so 1 is the quotient and 0 is the remainder. Similarly, 3 is equal to 0, 0, 1, 4 is equal to 0, 1, 0, 0, 5 is equal to 0, 1, 0, and so on. So these are different binary values which is equal to the decimals. But in case of the hexadecimals, when we exceed than 9, the 10th value will be A, B, C, D, E, and F. F represents 15, while E is equivalent to 14 of the decimals, and D is equal to 13, and C is equal to 12, and B is equal to 11 of the decimal number system. So this tables overall provides us a summarized way of the conversion of hexadecimals, decimals, octal, and binary to each other here. But when we convert the larger numbers, here you can see we have just 15 different numbers. So when we convert larger values, then we require certain procedures to convert that numbers, which will be in fact covered in the upcoming lectures here. Now this was the number systems relationships of each other. Dear students, this is the end of the lectures. Here is the book for you. You should study this book. This is very much good books over the number systems. The book title is Binary, Octal and Hexadecimal Number Systems for Programming and Computer Science, and it is written by Sunil Tanna. So you should download and read these books for the number systems. If you are interested in the programming, so then you must have the idea about the number systems. That's why the number systems is quite important. Also, if you have any question, you can drop the questions to my email, that is m.kadim@kust.edu.pk. I will wait for your question and will respond soon. Also, you can ask the question through the KCMS. You can post your queries over the KCMS and I will read your queries and will respond you soon. Thank you very much.